What are partial differential equations and why should you care? Welcome to another episode of the Touring Rabbit Holes podcast. I'm your host, Gabriel Hecht, and with me is your host, Dr. Alex Alanese. How are you doing today, Alex?
Doing well. How are you doing?
Excellent. I am thrilled to talk about partial differential equations. Boy, I'll tell you what. Actually, this episode is inspired by my attempts to explain to both family and friends and relatives why mathematics as a whole is cool, but specifically things like partial differential equations and the Fourrier series, as well as machine learning and how they use those tools. So I'm pretty excited about this episode. In fact, earlier this week, I was talking to a girl on one of the dating apps, Bumble or Tinder or one of those, and she asked what I was into, and I said I'm into podcasting, and I podcast about math and physics. And she asked me more questions, so I tried telling her about partial differential equations, and I could already see her eyes glazing over. So I thought, how can we explain these in terms that are understandable, so that people can appreciate them? So we designed this episode. Now, this episode also is inspired by a recent article that is blowing up all over the academic part of Twitter. Recently, there is a paper out about a technique to use machine learning to solve some notoriously hard math problems, specifically in partial differential equations, by using Fourier transformations. So, right. What do you know about said paper?
First of all, let me just say we're going to do this in less than 20 minutes.
Correct.
Because we're going to keep you interested.
Absolutely.
And second of all, yes, it's going to be, when we get to the end of it, we'll explain to you how machine learning is coming into the field of partial differential equations, which dates back to the 1700s, and people have been dealing with them without machine learning for quite a while successfully.
Yeah, exactly. And we are first going to talk about what is a partial differential equation. How is it different than an ordinary differential equation? We then are going to take some time and actually show you how to solve a partial differential equation using nothing more than what you would learn in a introductory calculus class.
Correct. So if you've had one semester of business calculus in your college, or even 1 year of high school calculus, we're going to show you how this goes. And I had the experience of teaching partial differential equations to my daughter when she had 1 year of high school calculus.
Yes. And so not only will you know how to solve them using basic calculus, we're also going to spend some time talking about why you need them. Why are they used in the real world? They're used in all kinds of things, including climate modeling or modeling finance in the stock market. So you'll know those. And finally, we will end with discussing the paper that uses machine learning and the Fourier transform to solve especially ugly and difficult partial differential equations. So yeah, it'll be quite interesting.
So let's get started. When my daughter had learned how to take derivatives, that's all you need, I showed her a partial differential equation. Now, historically, the first one is, imagine a contrived problem, but it's one that's easy to imagine. Imagine a 1 meter rod of stainless steel, say, and we're going to put temperatures on it. We're going to put a hot coal on it, an ice cube, a lens that's focusing the sunlight on it, and so we're going to have a profile of temperature that's like that, arbitrary. And it's along so it has one dimension along X, and then we're going to take all the heat sources off and start a clock. And how does the heat, the hot spots are going to eventually go diffuse into the cold spots. How does that temperature profile evolve with time? So there's a change with respect to time, and there's a change with respect to the x-axis. So that is a partial differential equation, because I have differential changes in the x direction and in the time direction.
Correct.
As opposed to normal derivatives where you just have y is equal to a function of x, and you're looking at slopes and just in one dimension. So now we're in 2 dimensions.
Correct. Yep. So we're tracking two things here. And as Alex alluded to earlier in this example, of course, following the second law of thermodynamics, objects that are hot, or rather heat, moves in the direction of colder areas. Did I say that correctly?
Yes. And so the heat equation was solved back in the 1700s, and exactly that problem which we just posed. And it turns out that the solution is, so we're going to cut away, and I'm going to show you the solution. I'm going to actually plug in the solution to the left, where I have the change in temperature with respect to time, partial U, partial T, is equal to some constant K, second partial derivative of the heat with position. And I'm going to plug in sines and exponential functions, and it's a little bit of algebra. You're going to go, wow, so this one function, if you plug it on the left and you follow those instructions, and you plug it on the right and you follow those instructions, you get the left equals right. You have a solution. Mm-hmm. That is the art of partial differential equations or ordinary differential equations. Is I have an equation with partial derivatives, first, second, seventh, partial ordered partial derivatives, whatever it is, and their pluses and minuses equals something on the right-hand side. Is there some function in the universe that if you plug it on the left and plug it on the right, they equal each other?
Yeah. And
machine learners are going to solve the really hard problems when in many cases, in fact, in most cases, you can't find the exact solution where it plugs in beautifully on the left and plugs in beautifully on the right. You do 6 steps of algebra, you go, oh, look, I have a solution. Yeah. And so we'll get to that. And you said, so what are the applications, right? You're interested in heat. Yes. You could be interested in stresses on a building, say, and it's as it's swaying in the wind, right?
Mm-hmm. Absolutely.
Or finance, right?
Yes, yeah. So in finance, what are the variables? Obviously, anything that changes in finance. So obviously, you'll have time derivatives as well
and pricing derivatives.
Yes.
So one of the oldest problems in finance was that people began to invent, in back in the 1700s, I believe, derivative instruments for farmers and for shipping people. For a farmer, you would have the problem of, boy, I really can't afford corn to go below $1 a barrel. Mm-hmm. So, and my crop is going to be ready in 3 months. So you would buy the ability to sell your corn for at least $1 3 months from now. Okay, I want to buy that insurance. It's mm-hmm. called a put option. How do I price it? And then the other option from the other side of it is, boy, I'm a trucking company and I can't afford diesel to go to $5 a gallon. How do I buy the right now, 5 months from now, to buy my diesel for that price or less? How do you price that? That was a centuries-old problem. Mm-hmm. It turns out there's a partial differential equation that is a transformation, believe it or not, of the heat equation, and it's called the Black-Scholes-Merton equation, and it prices calls and put options, and it got a Nobel Prize. The physicists unfortunately died, and you don't give them Nobel Prizes to dead guys. So, oops.
Yeah. Wow. Yeah, that's quite fascinating. So, in fact, every single video that I looked at in research for this episode brought up that equation. So that's a pretty famous partial differential equation. I
do believe that the options markets are 100 times more valuable or valued than just the normal stock markets.
Yeah. There's a whole lot of math and finance that we actually haven't done, both on the podcast, but also in my research as an engineer. So that's an area that I'd love to go into more, actually.
So one of the things that I found interesting and didn't finish, even after I finished my PhD in physics, mm-hmm. was I had statistical physics background and so on and so forth. But I didn't fully understand the following triangle that it didn't happen to me until I was actually on a trading floor trading derivatives. Let's think about stocks.
Okay.
They go up and down, right?
Yes.
They are stochastic. There's mm-hmm. no predictability. What's happened in the past is no indication of what's going to happen in the future, and you'll see they squiggle, right?
Yes.
Neutrons inside an old fat man bomb would bounce around before either escaping or causing a fission, and they piled up a whole bunch of ladies whom they call computers, and they said, okay, let's statistically calculate that behavior. If I release 1,000 neutrons and they're going to bounce around, how many of them are going to cause fissions and make the bomb go boom, and how many are going to escape? And that is something that touches partial differential equations, because neutrons diffusing is the same thing as heat diffusing in a one-dimensional rod. And the problem is, so now imagine this. You were taught how to take integrals. Remember how you did take integrals? You had rectangles below?
Yes.
And rectangles above?
Yes.
And you took the limit as the rectangles got infinitely skinny, and you got, if the upper and lower rectangles converged, that was your area.
Mm-hmm. Correct.
What do you do when one of the terms of the integral is a distribution, a bell curve, where as you move, instead of having a smooth function, you throw a dart and you pick, okay, that's a value, and then you throw another dart. Well, that's the value, and you throw another dart. That's what stocks are doing, aren't they? They're second to second. They're like, ooh, ooh, ooh.
Yes. So they're discrete. Is that what you're looking for?
Well, they're stochastic, right? Because they take unknowable jumps, but those jumps are being pulled from some distribution. Usually it's a normal distribution, and it could be another one, but it's usually pulled from some distribution. And so the problem of to solve a partial differential equation that's stochastic becomes incredibly challenging. And it turns out that there's three different ways you can think of it. One is as a partial differential equation. One is you have your Excel spreadsheet and you do a trinary tree, or there's a probability of the price going this way or this way or this way, and then a trinary and a trinary and a trinary, and you let that happen a bazillion times, and you get your distribution and your mean and your variance on it. You can do that, or you can do it with something called the Ito calculus. And so anyways, partial differential equation, a certain probability distribution, or a certain tree process, a trinary or above, they're all equivalent formulations. And I always found that to be fascinating. And I didn't figure that out until I was doing finance.
Oh, nice. That's really cool, actually. That's really cool. We should do a diagram for that. If you can think of one, we should do a diagram and cut away,
And so going back, and I want you to show your webpage.
Sure, absolutely.
Going back is, okay, what if I had set up the following problem in just algebraic, just an algebra. Imagine a graph. Here's the x-axis. Imagine that you're going 0, 0, 0, 0, and I jump up to 1, and I go across 1, I come back down, I go 0, 0, 0, 0, 0.
Yes.
That is I could imagine that's the temperature I set up for my one-dimensional rod. And it's going to evolve in time. If I turn off the heat source, it's going to come down. That has a solution in sines and in exponential decay. And what you're going to show on your website is that the first solution is a sine wave that almost fills in that square, right? Almost, but obviously not fully. And then you add a second sine that picks up a little more, it fills in a little bit more. And then a third sine that fills in a little more. So do you have it?
Yes, I do, certainly. Yeah. Now for our listeners and our viewers, if you go to the website, breakingmathpodcast.app, again, that's breakingmathpodcast.app, the very, very top, you will see applets that we have for you, which things, basically they are interactive math demonstrations. And then under applets, you can go to Fourier sequence and click on it. Now, when you open it, you'll see, it looks like a fishing rod or a stick that's spinning. And on top of that is a smaller stick. And on top of that is a much smaller one. And they're all spinning.
Right. The first one, the biggest one, is spinning slowest. The next one is spinning twice as fast. If you do more terms, you'll spin 3 times and 4 times as fast. And so what you're doing is you're approximating a square pulse with sines and cosines.
Yeah.
And I always imagine it this way. Beethoven's Ninth Symphony, the choral movement, the fourth movement. Imagine you had a bunch of tuning forks. And we can hear it at 20,000 hertz.
Yes.
So I have a 20,000 kilohertz tuning fork, a 19,999 tuning fork, all the way down to 1 hertz, and obviously not 0 hertz.
Yeah.
And if I tap on them fast enough, I can replicate with just these pure sine waves Beethoven's full Ninth Symphony, fourth movement. And obviously I'm going to hit some of them more often, some of them harder, some of them softer.
Yeah.
And that infinite series of sines and cosines is what you're showing in your website, which is beautifully done.
Yeah. And what's also cool on this website is you can adjust the amount of circles. Like if we type less, we can go down to only 1, or if we can increase it. Oh, and as we have fewer circles, the sine wave is more of just a single sine wave.
You get the first approximation.
Yes. And as we increase it, it adds a sine wave on top of a sine wave on top of a sine wave, an arbitrary amount. It gets closer and closer and closer to a perfect square. So that's a pretty cool little applet there. Good.
And so I think we should get to let's go to your paper and talk about why that's interesting.
Excellent. Yeah. So this paper blew up on Twitter, and I'm going to read the original article. Now, the paper that we shared on Twitter was from MIT Technology Review, and it was by, let's see here, it was by a Karen Howe, and basically she talked about a technique of machine learning, where it solves very, very complex partial differential equations, and it does so much more effectively than previous machine learning attempts. Now, the only difference with this one is that it solves them not in the time domain, which is the XYZ axis, well, XYZ and time axis, but rather it solves it in the frequency domain using a Fourier transformation. So how would you explain that to a layman who's never heard of Fourier?
First, I'd just go back to is common physics. If I had a singular tuning fork here and it was like 1,000 hertz,
Yes.
and I go and I tap it, I'd hear hum about 1,000 hertz.
Okay.
So if I graph that, assume there's no friction, that sine wave at 1,000 hertz would go on forever to the negative x-axis and forever to the negative to the positive x-axis. But what's another way to describe that same information is to say, oh, if I graph it as a function of frequency, then there's only one frequency, 1,000 hertz. So if now the bottom axis is frequencies, I go nothing. Oh, there it is. There's my tuning fork at 1,000. You and I are speaking. If I'm talking about Beethoven, it takes a lot of frequencies to put together what voice or symphony or music or so. The frequency domain literally is complementary to the time domain. So the time domain would be this, and the frequency domain would be that.
Yes.
If I had two tuning forks and I hit them, they would form a beat.
Okay.
But if I Fourier transform, I would have two frequencies. So in addition to that, they have the nice property that when it works, they turn your partial differential equation into an algebra equation.
Yeah.
And you just have to solve an algebra equation.
Yeah, and it's so interesting. I'm trying to explain, or even trying to understand why it is that for machine learning, even for machines, it's much easier to do it in the frequency domain than in the time domain. And this is where it's a bit beyond me.
Each side has its advantages. So time domain, like I said, if you have a problem that's complicated in the time domain, it may be that you transform it, and that's a Fourier transform, and get an algebraic equation. So what do I mean? If I have a complicated in the time domain here, if we graphed our voices, it would be this smear, right, on an oscilloscope.
Yes. Yeah, exactly.
If we go to the time domain, frequency domain, it might be there's just a few hundred frequencies that we're speaking on, and it would be an algebra equation. And you find roots of this algebra equation. The roots would be the frequencies.
Yes.
So that's one of the reasons that when it works, now it doesn't work all the time, the Fourier transform and the frequency domain is much better when it works.
Okay. All right. So that works.
So right. And so how did a CD contain hours and hours of music, or how did a DVD contain hours and hours of video? Because what you're packing in the suitcase, the disc, is just the coefficients of the sines and cosines. Literally, as it's spinning around, the computer's reading ones and zeros going, oh, okay, so imagine my example where I had the tuning forks from left to right from 20,000 hertz to 1 hertz. It's literally telling the computer speaker, I want you to do this, hitting the tuning forks this way, this hard. So you're packing in a CD, in something this small, you are packing a movie or a symphony. And that's because you did it in the frequency domain.
Yeah, it's okay. We failed.
So why do where is it that we need machine learning? We have a lot of partial differential equations that are complicated in multiple ways. One is, imagine I have a fixed X, Y, and Z axis in a grid system, and I have cars crashing, and they're deforming.
Yes.
And if I move in really tight on the pixel, I had an aluminum bumper filling in one, and now I have the steel bumper of the other car starting to squash into the cell. So is that cell still mostly aluminum, or is it steel? At what point do I cut off? It started off as all aluminum, and then the other car bumps into it. So you start having to cut off things, and you start losing conservation of matter and energy.
Yes.
And a machine learning system with neural nets might actually solve it in the same way that you catch a football. You don't go out and solve a differential equation for a drag and a football that's going through a medium called atmosphere and it's being dragged. You actually just run out and catch it.
Okay.
Your neural net catches it.
Okay.
You have an equivalent solution to the ugly solution of a partial differential equation. The other one is if you actually let the grid collapse because it's being crashed, and you had your delta Y and your delta X that big, and now the cell got squashed smaller, and you have problems that way.
Yeah.
So machine learners are doing exactly what our neural nets are doing. They're able to solve the problem practically, not exactly.
Okay.
And they do a good job of matching the actual physics experiments, and we'll show you that on that site.
Yeah. If you want to see a graphical representation of what this software does, or this software technique, there is a GIF, a graphical, I'm sorry, what does GIF stand for again?
And so that shows the actual experiment versus the predicted of a partial differential equation of turbulent behavior.
Yes, using machine learning, which uses the Fourier transform technique.
Right. Yeah. So with that, do we have anything else to say? Because we're going to try to stick from now on to 20
minutes
plus or minus.
Yeah.
Right. Let's cut it out then.
Awesome. All right. Well, thank you so much until next time. Thank you so much for joining us. And please hit the subscribe button. And if you want to email us, our email is touringrabbitholespodcast@gmail.com. You can also leave a comment in the video. We'd love to hear from you. Thank you so much.